the paper there? Okay, so let's look at the definition of a parabola from a slightly different perspective than we had before. First of all, let's define what a parabola truly is. You've been dealing with quadratic equations since Math 1. You know what a parabola looks like, but you've probably never actually been explained what a parabola is. A parabola is the set of all points that are equidistant from a particular line, which we call the directrix, right? Yeah. And a particular point, which is the focus in the plane. So we have two different versions that can be standard equations for our parabolas. We are used to the first one, when the x value is squared and the y value is not. We're used to that. Those either open up or down. We're used to that. It's either a U or it looks like a hill. It depends on whether there's a negative in that equation or not. Okay. Let's see here. And then, of course, if the y is squared, if we were to solve that for y, we would end up taking the square root. So you're familiar with that. So these either open right or left when the y is squared. Okay. Now, notice there are some variables in this equation that we're not used to. Now, h and k, you may have put a parabola in vertex form before, so that gives you the vertex, but you've probably never seen that p in there before, okay? The p is our focal length. Okay, that is the distance from the focus to the vertex. Okay, distance from the vertex to the focus. And what that does is it kind of dictates the width of your parabola. Okay, it dictates the width and kind of height, I guess you'd say, of your parabola. The focal width is the absolute value of 4 times p. So the width is always going to be wider than the length. Okay, the width is always going to be greater than the length. It's 4 times p, not just the p. Honestly, I can't guarantee you what they're gonna. I have seen them before on the exam a few years ago when there was free response still on it. There isn't anymore. It's all multiple choice. But one of the free response questions asked about the focal width of a parabola. So they may ask you that. So that's why I'm giving you all this information here. Now, let's draw a picture to kind of help us make a little bit more sense of this. And give us some examples of what these may look like. So I'm just going to put a random vertex over here. Here is, we'll say, this is the traditional parabola that we're used to seeing. But the focus would be here. The focus is inside of the parabola, and your directrix is the same distance away from the vertex as the focus is. So I've got the focus 2 units above the vertex, so the directrix is 2 units below the vertex. So this is a horizontal line, which is what we call the directrix. And the F there is the focus. Okay. So that would be one that opens up. That would be a positive x squared. Let's put one down here, and let's make it a little bit wider. The focus would be further away here. I probably should have used a different color because this directrix would be up here. This one goes with that one. That one goes with that one. Should have used different colors. But That's an example. So what this is, let's go back to the definition for just a second, now that I've drawn a picture. Okay? Your parabola is actually, if you measure the distance from any point on the parabola to your directrix and to the focus, those distances would be the same. So the further away we get over here, and the points further on this side are further away from the directrix. They're also further away from the focus, but they are the same distance from both of those. Okay, that's the technical definition of a parabola. Let's draw another one. Let's draw one of the y-squared ones. Let's say it's over here for its vertex. Okay, say it has focus here. I made that 3 units. 1, 2, 3. So its directrix is a vertical line. Okay, so that's an example of one where the y is squared. It opens to the right. It would be a positive y squared. And this distance right here is p, from the directrix to the vertex, or from the vertex to the focus. Either way you want to look at it, that distance right there is p. It's the same in the other one. I just forgot to bring up that point when we were doing the other one. And then the focal width, that 4p, is when you're at the focus, you measure to the sides of your parabola, okay? That would be the 4p. So I didn't draw it very much to scale, but the distance when you're at the focus from one side of the parabola to the other side of the parabola is the 4p. Okay, so that's parabolas from a different perspective than you've probably looked at them before. Now the next one will hopefully be review, okay, circles. Okay, these are all what we consider conic sections. Circles with a center of HK. I think you've probably heard this definition before. A circle is the set of all points that are equidistant from a particular point. Okay, all the points in the circle are the same distance from your center. Okay, and that distance is what we call the radius. Your standard equation, x minus h squared plus y minus k squared is equal to r squared. The center is positive h, positive k. You change the signs. They're not always positive. You just change those signs when you take it out of the equation. Okay, those minuses mean change the signs. Okay, the radius, we take the square root of that number, or that constant on the other side of the equation. And you know what a circle looks like. Let me just give you an example of an equation here. Let's do x plus 3 squared plus y squared is equal to 25. Okay, if that was the equation of our circle, we would be able to graph that. The center is at -3, 0, because the y didn't have anything that was being added or subtracted from it. And it has a radius of 5, so the easiest way to graph that is from your center, go up 5 units, go down 5 units, right 5 units, and left 5 units. And then make it look as much like a circle as you possibly can. All right. Okay, this is new. Okay, this is new. An ellipse. Okay, an ellipse. It's kind of like an oval. When we graph it, you will see that it looks like an oval. But what's going on with an ellipse, its technical definition is that it's the set of all points in a plane whose distances from two fixed points, we call those the foci, in the plane have a constant sum. Okay, so that's why these equations, you have a plus in between them, and they're always equal to 1. Okay, they're always equal to 1. So That's what that equation is representing, is that the distances have a constant sum. The center is halfway between the two foci, okay? So we can do this two different ways. We can have an x minus h squared over a squared, and or we could have y minus k squared plus x minus h squared. Here's the difference, okay? A is always greater than b, okay? A is always greater than b. So when the x term is over the bigger number, so the first one that we're looking at, it has a horizontal orientation, okay? That kind of makes sense. X is always horizontal. It has a horizontal orientation, or you can look at it as it's wider than it is tall. Okay, it's going to look more like a football. Okay. If the y is over the bigger number, is over the a, then it has a vertical orientation, and so it is taller than it is wide. So think about an egg sitting in a carton. Okay, it's taller than it is wide when the y is bigger. Okay. With ellipses, we talk about the focal axis. Okay, so when it's horizontal, think horizontal line. So the focal axis here is y equals k. For the other one, when it's vertical, vertical lines are x equals, so those are x equals h for the focal axis. Okay, the vertices, here's what we've got. For the first one, we've got h plus or minus a, k. Okay, they're centered on that line y equals k. We start at the center, we add the a, and we subtract the a, and that's where our vertices are going to be. For the other one, they're centered on that vertical line, so the x-coordinate is always h, and they are k plus or minus a for the vertices. All right, so let's talk about what this looks like here. Let me draw an example of an ellipse. I'm going to put my center here at HK at 0, 3. Okay, I'm not working off a specific equation. I'm just drawing an example. So this is going to be my focal axis. My vertices, I'm going to say that A is 3. 1, 2, 3. So I have a vertex there, and a vertex here. And then depending on what B is determines how tall it's going to be. But then I'm just going to sketch this in here. Okay. There's a rough sketch of an ellipse. So this point right there in the middle is the center, and these are the vertices. Okay, those are the vertices. Okay, similarly, if I had one that was vertically aligned, let me just put a center here, and so then my vertices are going to be on that vertical line. So I'm going to put them 4 units away. Okay, this would be my focal axis coming that goes straight through the center and my vertices. And let's make this one a little bit skinnier. Okay, there's my ellipse there. Kind of looks like a germ or something. Yes, ma'am?
You got a circle. Why aren't you doing it on the 2 points on the outside?
Okay, so this is because it's not a circle, it's an ellipse. So these are the vertices. The vertices are inside of the ellipse. They're not actually on the edges of the ellipse. It depends on, let's see here. I have never seen them actually ask you to graph it. I've really only seen them ask questions about, like, what is the location of the vertices. I've never actually seen them ask anybody to actually graph one. Because with these conic sections, we can't, you can, it's just not pretty to be able to solve for y in order to be able to graph them in our calculator. So I've really never actually seen them ask you to graph them. They just ask you questions about the other side. Okay, any other questions? I know this is a lot of information at one time, but I just want to give it to you and then we'll look at how to use it here in a little bit. All right, last one, a hyperbola. Okay, a hyperbola. A hyperbola is the set of all points in a plane whose distances from two fixed points, the foci, have a constant difference. Okay, they have a constant difference. So it looks very much like the equation for an ellipse, except this time we're subtracting. Okay, that's how I keep them apart. And the way that I think about it is the H has that line through the middle, so that makes me think of a subtraction sign. An ellipse has, has more lines in the letter E, so it's plus. It's not a very good way to remember it, but it makes sense in my head. And again, the center is halfway between your two foci. So the same rules still apply when the x comes first, or the x is, well, in this case, the x comes first. Okay, your orientation is going to be that it crosses the x-axis. Okay, when the y comes first, it's going to cross the y-axis. So since we're crossing the x-axis with the first one, our focal axis is going to still be y equals k, and for the other one, it's going to be x equals h. Our vertices are in the same places as the other one. It's h plus or minus a, k, and then this one is at h and k plus or minus a. Hyperbolas have asymptotes. They actually have two. They have two slant asymptotes. And here's their equation. Y equals plus or minus b over a times x minus h plus k. And the other one flips it over. Y equals plus or minus a over b, x minus h plus k. I've never really seen them ask a question about the asymptotes, but I wanted to throw it out there because it is a fact about it. Here's what hyperbolas look like. They kind of look like two parabolas facing in opposite directions. So let's say we've got one that looks like this. Okay, the focus is still inside of the hyperbola. And it's going to be completely symmetric. So the other one, that's not symmetric. It's supposed to be 1, 2, 3. 1, 2, 3. There we go. Okay. Focus right here. Okay, they're the foci. So the distance from all the points to the foci are the same. Okay. So this would be our focal axis. This would be the y equals k. And our asymptotes are slant asymptotes. So they asymptotes are always dotted. Get it right. Okay, just like with our rational expressions or rational functions way back when. Okay, it gets really, really close to the asymptote, and that describes its end behavior. Okay, so that's that one. If it crosses the y-axis, here's an example. Got foci. Here's the center. Here's the x equals h for the focal axis. And then these would have a much steeper asymptote. Okay, one more thing that I need to go back and mention is one more kind of vocabulary. This would be the major axis, okay, the axis that it crosses. It kind of makes sense. This would be the major axis. This would be the minor axis, the one that it doesn't cross. Okay, major, minor. We can also talk about that with ellipses. So go back to your ellipses really quick. The major would be the one where it's bigger. Okay. So this would be minor, and this would be minor. Okay. Major is where it's bigger or where it crosses. Minor is where it's smaller or where it doesn't cross. Okay. Let's see here. I think I've covered everything that I